Okay, in this video I'm going to compute the expectation for a Poisson random variable. And remember that if a random variable x is Poisson, then that means that the probability that x equals k is lambda to the k, e to the minus lambda over k factorial. And that is the case for k equals 0, 1, 2, etc. Remember that the Poisson random variable is a version of the binomial random variable, except that you're dealing with a continuous time interval rather than a finite number of trials. So this counts the number of times an event occurs, and that can be any non-negative integer. Now we want to compute the expectation, so as usual, that is going to be the sum of the possible values times the probabilities. You're probably sick of hearing that, and if that's so, then I'm doing my job. I want to drill that into your head. I got the possible value, and then the probability of that value I want to go ahead and put in. Lambda to the k, e to the minus lambda, all over k factorial. Okay, now what I'm going to do here is something very similar to what we did in the binomial distribution, and that is fudge things around until we're left with a sum of total probabilities for another distribution. Okay, so as before, I'm going to notice that this term with k equals 0 doesn't really contribute anything, so I can instead sum from k equals 1 to infinity. I'm going to have the k there. Now to cancel that k, I'm going to break a k off of the k factorial. That'll leave a k minus 1 factorial still hanging around. And I'm also going to break off a lambda so that it'll float out to the front of the distribution. And then there's an e minus lambda, e to the power minus lambda there. Okay, the k's cancel, and the lambda will be brought out of the summation to give the sum from k equals 1 to infinity of lambda to the k minus 1 e to the minus lambda all over k minus 1 factorial. And now I'm going to do the same kind of trick as before. I'm going to substitute a new value in for k minus 1. So that'll be lambda, and then my sum is ranging from 0 to infinity. Okay, because I started at 1 last time. This time I'll start at 1 minus 1, which is 0. And infinity, that's just saying we go on forever. If every value decreases by 1, we still go on forever. And then that's lambda to the m, e to the minus lambda, all over m factorial. And this summation here, I don't even have to define a new random variable. It can be the same random variable. I've just put in a new letter. I've put in m. And notice that I'm using m instead of k. And this, without the sum, each of those terms would just be the probability that a Poisson random variable with parameter lambda would be equal to m. So if I sum all those up, that gives me total probability, which has to be 1. And by the way, I can't resist, once again, if you pull out an e to the minus lambda, and I sum m equals 0 to infinity, lambda to the m over m factorial. Those of you that have been working with calculus recently might recognize that as the infinite series for e to the x to the n over n factorial. Okay, so you have e to the minus lambda times e to the lambda, that gives you 1. An alternative description that doesn't refer back to the probability distribution. In either case, and again with this description, if you didn't understand it, that's just fine. In either case, we get that the expectation of the random variable is just lambda, the parameter.